then let's get started. So it's my great pleasure to introduce Sudharshan Suresh. This is his thesis proposal. So Sudhu has been in my lab for several years now, first for his master's and now for PhD. And he's actually been at CMU longer than that. He's been here as a risk scholar over summer, working with Red several years ago. And yeah, so it's my great pleasure to announce his talk on tactile SLAM, perception for dexterity via vision-based touch. So he has done some really great work recently over the past few years on using tactile sensing to do localization and mapping. And so he will do a talk. Please only ask clarifying questions during the talk. Short questions, and then afterwards we'll start with a committee for questions, starting with external members and then internal, and then we'll open to the audience. Okay, with that. Oh, and I would like to thank the committee for being here. So in particular, Nancy Pollard, Shubham Tulsiani, Mustafa Mukaddam, and Alberto Rodriguez. Okay, Sudhu, please go ahead.
All right. Thank you, Michael. So good morning, everyone. Welcome to my thesis proposal talk. Like Michael mentioned, I'm Sudharshan Suresh. I'm a PhD student at the RI, and my thesis is titled Tactile SLAM, Perception for Dexterity via Vision-Based Touch. Firstly, I'd like to thank the committee, my advisor, Michael, the members from CMU, Nancy and Shubham, and our external members, Mustafa and Alberto from MIT. But yeah, so I'd like to start out by motivating our work in tactile perception. Robotics researchers are no longer averse to contact anymore. In fact, they embrace it. The community as a large part of this audience included isn't just doing pick and place. They're sliding, they're grasping, they're pushing, they're bumping, reorienting, and gating across objects. And there's a large amount of information at the distal end of these robots that is being underutilized. Humans, however, are remarkably adept at utilizing their sense of touch. We can feel for our keys in our pockets, for example. We can trace our way down a corridor in the dark. And one example here is just me rummaging through the top shelf to find my mug, tracing the boundaries of it until I find a graspable handle. And this is considered a haptic apprehension problem. Research also does show us that perceiving global object shape is of great importance for performing everyday tasks. If you give a human something like keys, they can easily trace it out and figure out what they're having in their hands. And you could say the same for dice and many other small objects. Despite all of this, vision still remains to be a dominant percept for estimation tasks. For example, you can look at like the sort of famous OpenAI cube manipulation problem, where they use a highly engineered multi-camera system to get tracking information for these. And over-reliance on these systems may not be practical for robots in the real world when we see them deployed in households and kitchens and so on and so forth. The fact of the matter is, with a disposition towards interaction, occlusion is really inevitable in these cases. And this can be due to self-occlusion by, say, a robot arm over here, or occlusion from clutter in a scene. And in addition to this, there are also a multitude of scenes and objects for which vision simply may not work. So you can think about transparent objects, specular objects, and so on and so forth. Over the past decade, we've seen robotics being dominated by tactile sensing solutions. These can include vision-based tactile sensors, such as the gel site or the digit, large, soft, compliant grippers that you can use, tactile skins that can be fit across a robot's periphery. And then we also have sensors such as the biotech, which are biomimetic tactile sensors in these cases. And these have been specifically designed to maximize the amount of information that we can get from these interactions that we have with objects. However, even with these advances in the sensing, the underlying inference of these using these sensors is still an open question. So you can think about what sort of signals can we use for spatial perception tasks? How can we integrate this information with other modalities that we have? And how can we efficiently process this dense data in real time? The next question is, what latent or spatial information do we want to infer with these sensors for objects that we work with? So examples of these can be trying to figure out material properties or shape, stiffness, elasticity, frictional properties, and even semantic object classes to an extent. In this talk, we will focus on a spatial perception task, or getting knowledge of object shape or pose. And this can be information that can directly enable downstream planners, state-based policies, and controllers. So you can think about knowledge of geometry and state to help a wide range of applications in everyday household robotics and warehouses. And this is especially important in scenes lacking a priori object models, where robots must continually learn from interaction. You can think about common actions such as grasping and clutter, trying to singulate these objects, insertion. All of these require some sense of geometric knowledge. Now I'll present what our thesis statement is, along with some distinct directions of work that we've been undertaking and plan to do. So concretely, our goal is, given a posed tactile stream, we would like to reconstruct 3D models of objects just as we would with a camera. The long-term goal of this is to build towards a manipulation stack that can be built towards a perception module that can be incorporated in a manipulation stack. And to give this precise information of objects can help things like grasping, regrasping, insertion, and in-hand manipulation. This can be viewed through the lens of a SLAM problem. And to extend this analogy, you could think about robot proprioception, gives us odometry, just similar to how encoders would give us odometry for mobile robots. You can think about visual perception from vision-based touch that can give us similar camera measurements that you can get from robots. And finally, any of these reconstruction goals can be compared against object meshes, similar to floor plans that you get in mobile robots time. However, alongside all of these, there are some unique challenges that tactile SLAM does present. The first one is locality. Tactile images lack global context that you can get. If you take a picture of a mug with a camera, you have a wider field of view that you can actually use to associate between frames. But with tactile sensors, you are essentially looking at a direct window of the interactions. The second one is inclusivity. While conventional cameras passively observe a scene, tactile sensors actively perturb them, or more rather, tactile sensors attached to a disc lens, so the robot is actively perturbing these scenes. And the last part is coverage. Given their small form factor, it may not be possible to get full object coverage. So if we think about how to represent these objects, we'd have to figure out a way to faithfully approximate regions that we have not seen or felt before. Alongside these challenges, we also have certain research opportunities at this juncture in robotics research. The first one is there's affordable and commercial vision-based touch and tactile sensing that gives us high detailed information of these interactions. For example, you can think about the digit and the gel site, which now come at accessible price points for robotics research, open source designs that you can even self-fabricate. And these serve as a window into local interactions, basically being cameras embedded inside these elastomeric gels. The second part is that realistic tactile simulation allows us to learn measurement models from simulated interaction, which gives us a breadth and diversity and scale of interaction that is unachievable with real robotics. In our work, we highlight the transfer of these models to the real world, as I'll talk about. And finally, the success of using neural fields has shown great promise in dealing with images from perspective camera models in the real world. And in our proposed work, we delve into extending these methods to work for tactile perception problems. I'll keep this Venn diagram a constant in the proposal as we sort through the different as we sort to SLAM with tactile sensors. So some of these methods focus on the assumption that we have object tracking, where we can just focus on the reconstruction problem when we get tactile sensing. Other methods assume that we have known object models, where we focus on robot object localization tasks. And finally, down the middle, we depict the full SLAM problem with minimal object-centric assumptions. In terms of the completed work that we have, we first present ShapeMap 3D, which is geared towards efficient object reconstruction with the gel site and RGBD data. Following which, I'll switch gears to talk about a localization problem called Midas Touch, where we are tracking object pose distributions of a robot finger using vision-based touch. And finally, a precursor to our proposed work is a full tactile SLAM implementation for a simpler 2D planar problem. And after this, in some proposed work, we'll talk about neural tactile SLAM, which is building these online reconstruction tasks using neural fields and the promise and potential that it shows. And finally, to close the loop, we'll talk about how to do pose estimation in these neural fields, and using this for a 3D tactile SLAM problem. And I'd also like to thank all the collaborators for these works, as you can see pictured here. So keeping this Venn diagram, we can discuss some pre-existing work in this domain. So in reconstruction with touch, a lot of the initial work, such as that of Dragiev et al., focused on mapping techniques with discrete touch. This was later built upon for more accurate maps with vision-based touch, such as work by Bauza and others. In localization problems, the initial methods focused on using particle filtering-based methods, such as that of Koval and others, where they're getting discrete sensing at the end effectors of their arms, and they're trying to locate known object models that they have. Further using these results from you and others, and Lambert and others, work on fusing these with visual estimates that you can get from tabletop manipulation scenes to sort of solve the planar manipulation problem. And finally, vision-based touch gives us richer localization signals for pushing, such as work from Sodhi and others, and small part localization that you can see work from Belt and others, which use vision-based touch information for this localization task. And looking down the middle, there have been simplified versions of the tactile SLAM problem with constraints on the motions and geometries that they can work on. For example, Moll and Erdmann initially proposed a structure for using two planar palms to reconstruct a smooth convex object. You and others later extended these ideas for a batch SLAM implementation for planar pushing. And finally, with vision-based touch, there's been work by Sodhi and others to work for local surface patches that you can reconstruct over time. So there still is some sort of opening in terms of reconstructing full-scale objects such as YCB objects, and vision-based touch and all of the opportunities that I mentioned before are things that we would like to go into in proposed work when I talk about this. So all of this sort of is illustrative and sets the lay of the land of what exists in pre-existing work. And for more detailed information on this and the citations, I'd encourage you to look at the thesis document. So first, we'd like to consider the problem of object reconstruction from touch. This work, titled ShapeMap 3D, is done in collaboration with Zealand and Wenjin from the RoboTouch Lab, Joshua from BYU, and my advisor, Michael. So given a pose stream of tactile information and vision, can we incrementally reconstruct a priori unknown objects that we have here? Note that the sort of phrase, given a pose stream of tactile, given a pose tactile stream will be a common refrain to this talk. ShapeMap 3D here fuses tactile images that we get along with vision and robot kinematics to build implicit surface models of these objects. For example, here we have the bleach cleanser object. We have our robot circumnavigating it, collecting tactile information, and fusing it with an RGBD camera that is off display over here. And we also have uncertainty information that we can derive from this to use potentially for planning tasks and actively construction tasks. To sort of back up first, the first challenge we have here is deriving 3D information from touch. So the vision-based tactile sensors perceive contact geometries as images. The soft illuminated gel pad deforms elastically on contact, and it is captured by an embedded camera that we have inside. So the success of using supervised learning for RGB data to give us monocular depth estimation has motivated us to extend this towards tactile sensing. For example, here we have a convolutional network that uses RGB and ground truth depth information to sort of learn this mapping. We can do the same with realistic tactile sensing, such as TACT or TAXIM, where we generate a large corpus of interaction data to supervise the residual network. So here, for example, we can take a class of, say, 40 YCB objects and densely sample them for tactile information. And we can get the rendered tactile images here, along with height maps that we can use for training. So you can see that it basically mirrors the same monocular depth network. And supervising for reconstruction loss, we can learn mapping from image to 3D. And here we see some of these sim to real transfer generalization for this. For example, we have digit interactions that I have with these YCB objects. We have images and the resulting height maps and the thresholded contact maps, along with the 3D geometry that we can derive, which works well for small patches, for edges, and even for smaller textures that we can detect. We can also see the same for working with gel site images, going from gel site images to height maps to contact. The second challenge is, once we have this information, how do we incorporate this into a holistic map, combine this into an object-centric representation? And to this, we turn to SDFs and implicit surfaces, which have been a useful representation for robotics. They are easy to update, they are a continuous representation, and the gradient information, it can be useful for controllers and planners. As seen in this figure, the surface is the zero-level crossing of the object's estimated SDF over here, which can be derived from marching cubes or other methods. We can approximate this, and in this work, we choose using a Gaussian process, or what is formerly known as the Gaussian process implicit surface here. The one challenge in this work is that just using as is scales poorly to the dimensionality or the number of contact points that we get from dense tactile sensors as well as vision. And this is mainly compounded due to the fact that matrix inversion is expensive. One insight in this work is to break this whole inference problem into local updates and queries in a graph structure. This allows us to reconstruct, for example, say this 2D Stanford bunny with measurements that we get to get SDFs, uncertainty, and this is just a visualization of how these graph updates are happening. In the interest of time, I'll omit all these details, but I'm happy to answer questions. But the high-level picture is that we can update these reconstructions incrementally with this large amount of information that we're taking in. And here's the same toy problem for the real 3D Stanford bunny, where we incrementally add these small contact patches, and we're fleshing out what the STF is, along with the uncertainty information. And now I'll start to show you how these work with vision and touch information. So here, for example, we're doing simulation reconstructions with the ShapeMap 3D data. We have partial depth map information. We have these contact patches that we derive from gel site interactions. And we have the implicit surface along with the uncertainty that we get. So here we're taking two YCD objects, the bleach cleanser on the top and the tomato soup can on the bottom. And just for some metric results, we can observe a reduction in the tamper distance that we have with respect to the ground truth, which is usually a symbol of how reconstruction loss is. And at the same time, we can also observe that we have graph update and query times that are near constant. In the real world, we can see these interactions with two YCB objects. Note that here, all of the actions are pre-generated. We are merely circumnavigating the object and collecting this information. But one exciting potential for this is you can use uncertainty information to actively guide this, this whole procedure. Additionally, we also release these real and simulated object interactions as part of a data set that we call YCP set. So the takeaways here are we have an incremental method to go from vision-based touch and RGBD to object STFs and implicit surfaces. And we'll hold on to these ideas for the proposed work, where we introduce an alternate method to do the underlying optimization. We next switch gears here to talk about another cog in the wheel, which is the localization or place recognition problem. So this work is titled Midas Touch, or Monte Carlo inference over distributions across sliding touch. And it's done in collaboration with Sudharshan Suresh at AI, along with Celia in the RoboTouch lab, and my advisor, Mike. So sticking to the same idea, given an opposed tactile stream from a robot finger, can we figure out where we are, given we know what these object models are? And you can think about this being beneficial towards tasks like in-hand manipulation, regrasping, or gating along objects, where we really want to figure out where we are on an object surface. With Midas Touch, what we can do is track an evolving distribution of poses on an object. For example, here in this animation, we have the YTV sugar box with a ground truth information on where the tactile sensor is, along with pose particles, which are here represented as points, but are SE3 poses. We also have the trajectory that the sensor will take, along with images that we derive from the tactile sensor and the 3D geometries we derive from a depth network. So to see it in action, for example, we see one example of me interacting with this YCB sugar box object. We're sliding along. We can see that as we keep sliding, we can, once we hit a discernible edge, we can quickly collapse on what the position and orientation of the sensor is. And after that, it becomes more of a local tracking problem. So at a high level, what Midas Touch is doing is it's using 3D surface information that we get from tactile sensors, compactly summarizing these to embeddings that we can use to query, and using these to disambiguate over a long time with a particle filter. The first step in this process is something that we've already talked about, which is going from image to depth information, which I covered in the Shape-Found 3D. And here we're reporting it to you. Well, in that section, I worked on gel side images. Here we're working with digit images, which give us these local 3D geometries, for example, given an image interaction here. Once we have those geometries, we'd want to figure out a way to condense these point clouds into compact embeddings that we can use to figure out where we are. And this has a lot of analogies to the loop closure problem that you can think about in SLAM. So to look at what a good signal is for this place recognition task, we'd want similar geometric features, such as edges over here, to give us similar latent embeddings. So just as we can do in point cloud literature in the LiDAR domain, where there's examples of work that use sparse 3D convolution to quickly go across geometries and derive embedding informations that are compact and succinct. So you can think about these 256 dimensional embeddings that we can have, after which all of these retrieval tasks are merely just a dot product. And here we interestingly use these pre-trained models that work with LiDAR data, which are point clouds from another domain. And we further fine-tune them with tactile simulation data that we get. So we can go from images to embeddings. So to show you what that looks like, here's a visualization of the TSNE color maps of the embeddings on all of these objects once we densely sample poses. And the idea is that similar colors indicate similar embeddings that are close together in cosine distance. So when we look across all of these objects, we can delineate local geometries. We see edges on the sugar box to have a similar color, ridges on the power drill, for example, having a similar color, colors across the edges of the scissors, and even the threads on the baseball over here, which have similar colors, which essentially show us that there's similar geometric information, which can serve for pose supervision for these problems. Once we have these learned embeddings, we'd like to put this together in terms of a measurement model. So we have pre-generated dictionaries for these objects, given we know them, such as, for example, the power drill over here, where we densely sample these and get embedding information for all a large set of poses. And after which, if you want to figure out where we are, it's merely just an SCG lookup on that, and then a cosine product. The final part of this is combining this learned measurement model with what we have as a conventional particle filter down here. So incorporating model constraints, which is censored poses that we can assume we get from a manipulator, along with prior belief information. So this gives us downstream tracking that we can get. We can run nominally at 10 to 15 hertz, for example. Here, if we have the power drill, we go across the entire trajectory and we can quickly figure out where we are in the surface. To evaluate all of this, we collect a large data set called YCB slide, which consists of 500 simulated and real trajectories over 10 different YCB objects, along with ground truth tracking. So these are examples of some simulated and real trajectories that we have. All the green points here are the point cloud information that we derived from the tactile sensor. So here's another example with real data on the bleach cleanser object, where we can see the pose is ambiguous until we hit discernible features such as an edge. And once we quickly eliminate all these candidates, it merely becomes a local tracking problem beyond that. Here's another interesting example from simulation data, where we show how our method can capture multimodal distributions. So we can think about a symmetric object such as the mustard bottle, and we end up with two antipodal pose candidates here. And the pose error in these cases would be high, but we are inclined to think about this as a feature rather than a bug of the method. So for completeness, we also have some final pose results that we have here. And the general error trends that you'd want to look at are going from initial error to final error after running a trajectory, and a drop in this information, a drop in this error by a magnitude for the trajectory. And we can show that for the simulated and the real data that we have. So the takeaways from this is a method that we can use to go from touch to embeddings, inspired by mobile robot literature, and a framework to integrate these in a non-parametric filter for pose distributions that we can get. Finally, we'd like to give a small taste of the full SLAM problem, but on a simplified 2D setting. This work is titled Tactile SLAM for planar manipulation, and it's done in collaboration with Maria, Peter, and Alberto from MIT, Joshua from BYU, and my advisor, Michael. So given a forced tactile stream, in this case, forced torque information that we get from a simpler planar problem, can we estimate both object shape and pose in real time? Our approach alternates between mapping and localization steps. And this is similar to a tracking and mapping problem common in SLAM literature. So you can think about methods like PTAM and OrbSLAM, which have tracking threads that run at a much higher rate than the localization, than the mapping threads that we have. We've discussed this reconstruction pipeline ad nauseum, which is the implicit surface method, to derive this information. But for local tracking, what we want to look at now is a factor graph-based method where you can think about object poses. So you can think about successive time steps of x1, x2, x3. And we want to think about residuals informed by physics and geometry that can help us figure out where we are. So one example of this is a sense of odometry. So we can derive this from a planar problem because we have quasi-static pushing constraints. Another is an example of geometric validity. So when we're pushing an object, we'd always want to stay in contact with this. And this is derived as an implicit surface contact factor. But here we're always using the best estimate of what the shape is derived from the reconstruction problem. And finally, just to ensure that during non-contact, we have no penetration, we encourage non-penetration over here in terms of when we have two pushers and we don't have contact with one of them, we'd want it to stay outside the object. Finally, we add pose priors and some additional grounding constraints to give us an inference problem that we can run in real time for localization. So here's some examples from simulation with a circular prior and known initial pose. we can build the shape of these objects while accounting for its pose. For example, we have a planar rectagon object and a hexagon, and we also have an ellipse over here. The GPIS representation we have here is smooth and generalizes well to these arbitrary objects. In the real world, we consider a single pusher to circumnavigate, say, a square object over here. So here we have a post-torque sensor attached to a robot. And we first observe results from one such trial. While we recover shape and pose over here, it is less accurate compared to the simulation results. And this is primarily due to the lack of second pusher. So the more contacts we have, the more information we can get, and the better we can ground these problems. And we also have motion model uncertainties in this case. We conduct a second experiment where we periodically add global pose estimates. So you can think about vision giving us this periodically in terms of having a camera tracking. And this is a proxy for what is a more difficult multimodal task. And in this case, we see better shape estimates that we can get over time from touch and vision. So the takeaways we can get from this are a shape and pose estimation problem from touch, for a simpler planar manipulation problem to motivate the full 3D problem. And we'll revisit this idea of tracking and mapping in the proposed work that we do. So moving on to proposed research. Looking at the Venn diagram of what the related work is, in our proposed research, we aim for a system that is online, real-time estimates that can be useful for downstream tasks, one that is generalized to work with multi-contact dexterous interactions, and finally, one that is adaptable, that can be easily bootstrapped with vision, with domain-specific priors and pre-training. So the first proposed work we have is on tactile mapping with neural fields. We believe that this is more adaptable an approach compared to the Gaussian process work for shape reconstruction with initial final detail reconstruction that we have, and can also be further run online. So to motivate this, implicit methods have found traction in room size scenes for SLAM problems. And what they do is cast the reconstruction problem as an online optimization of a lightweight neural field. So methods such as ISDF can use a neural field to represent SDF information from a mapping with no poses problem, or we can look at IMAP or NISLAM, which essentially have tracking and mapping threads running, but they're optimizing this lightweight neural field. We're interested in extending these ideas and these formulations to vision-based touch for spatial mapping through interaction. So you can think about the same set of images that we get here, again, a perspective camera, the 3D information that we get from interaction, and how those play into building these spatial models for these objects. While both of them are perspective camera models, they are applied to very different domains of data. So, for example, we have photometric stereo sensors, which impose their own illumination on the scenes, whereas what we get from RealSense type cameras is natural color that we can use to associate between frames and do matching. There are different field of views. So we can think about millimeter range problems that we get from tactile sensors versus meter scale problems that we have working with RGBD type sensors. And the last problem is that in natural images, depth discontinuities are along occlusion boundaries. For example, between where the lectern ends and the floor begins, there would be a depth discontinuity. However, when we do with tactile sensors, we'd have all non-contact regions, for example, around this little blob over here, to essentially be depth discontinuities. So we'd have these across every single frame that we get, which is an additional challenge when we're using reconstruction laws from depth. So simply put, what we want to do, given a whole stream of tactile information again, along with intermittent visual estimates that we get from, say, a camera tracking the scene or this interaction, can we use these lightweight models or optimize these lightweight models on the fly to solve a surface geometry problem where we get an implicit surface and an online object STF that can be later utilized for downstream tasks. As a proof of concept, we first performed this online optimization of a single tactile frame. So here we have a single tactile frame by impinging on the surface of the power gel object that we have, along with the depth that we derive from it. The loss information that we get is derived from back projecting the rays and adjusting network weights to fit a truncated SDF loss. So here we can see the same visualized in terms of that compared with the ground truth information. And we can see that this already captures the finer details that we couldn't get from a Gaussian processor kernel type work. And we believe that the optimizing for these weights is a more flexible and adaptable way to do this. So here also pictured are the rendered normals that we get from optimizing over a set of iterations. And we also have the depth that we get, which matches up well with what the ground truth is. Here is another example running the online optimization over an entire trajectory of the YCB slide data that I talked about. So here we have the power gel object, and we're essentially running a course over the object with the sensor, and all of this is simulation data. And we can here reconstruct finer textures, ridges, and general shape that we can get from sliding across this object and incorporating these image keyframes. So once we have a method to map an object that we know we are tracking, or an object that is fixed, we'd like to close the loop and discuss the last part of our proposed work, which is neural tactile SLAM, which is, you can think about as an elder sibling of the planar tactile SLAM problem. With this improved method that we have for scene representation, we'd now like to go back and briefly talk about some ideas for the localization problem, where we preserve the same idea of operating with the localization mapping threads, similar to the problem. But unlike the planar problem, we lack these neat quasi-static pushing constraints that we get to sort of ground the problem and serve as localization cues. And to our knowledge, there is no work that utilizes Dexter's perception to reconstruct a priori unknown objects, which is where the opportunity lies. So zooming in on this, some ideas that we aim to investigate here for pose estimation from these multi-contact configurations are tracking in neural fields. So camera and sensor tracking in these neural field type work, where I talked about IMAP and NiceSlam, are well engineered and run at a higher frame rate than what the mapping threads are. There's also work for frame-to-frame tracking based on prior work in-hand tactile manipulation, such as work by Sodhi and others, that we'd like to incorporate for getting cues from one frame to another. And the scale of this information, or the how much more informative this problem is, amplified because of the fact that we have 4 contacts rather than 1 when we deal with, say, an Allegro hand. And the last part is we also want to incorporate global pose estimates that we can maybe get from an off-the-shelf tracker for these objects, and combine this intermittent, noisy, somewhat occluded information into the whole pipeline. So to just briefly touch upon one of these, so when we think about tracking with neural fields, such as works from IMAP and NiceSlam, they have a tracking process that is separate to this, which runs at a much higher frame rate. So you can think about this running at 10 Hertz versus the mapping process at 2 Hertz. And what essentially happens is they would freeze the scene. So freeze the scene network weights and optimize for the pose variables over these small displacements. And it tends to work out for full SLAM problems, which is what we're motivated to track. And lastly, after these 2 proposed works, I'll talk a bit more about what we want to apply these to, or what kind of data we'd like to collect. So we aim to evaluate all of this proposed work on a data set that we call DexTouch, where we would like to collect multi-finger interactions with an Allegro hand, retrofitted with digit sensors at its tips. So here we have 4 contacts rather than the one that we've been dealing with, and the sliding and the ShapeMap 3D work. Simultaneously, we'd also want to prototype these in simulation through a tactile simulator. And given the success in recent work in Allegro teleoperation, we'd aim to collect this data with a human in the loop. And a very preliminary version of this is shown in this video, but there's still a lot of work to be done in terms of tracking. But there have been a lot of work more in the learning literature that kind of does the telekinesis or the teleoperation problem with the Allegro, and we'd like to get inspiration from that. So you can think about simple hand tracking with one RGBD camera or two RGBD cameras that can give us good estimates of finger pose that we can remap to the Allegro to get this data. In terms of a research timeline, through fall next spring, we plan to work on the tactile mapping problems with neural fields and the collection of this DexTouch dataset. Between spring and summer 2023, we will focus on the tactile SLAM problem. And we'd like to preserve the same data that we have with the ground truth information for doing this pose optimization. And finally, the residual work along with the thesis writing will be in fall of next year, potentially graduation in late fall, depending on how research progress goes. But yeah, I'd like to thank all the committee here for attending this talk and the audience as well. I'd further like to thank all my collaborators and for Meta AI for being a sponsor for this research. And I look forward to the next year plus of research. I'd be happy to take any questions now from the audience here, committee members, and everyone on Zoom as well. Thank you.
Thank you, Sudhu. Really nice talk. Let's start with questions from the audience, and we'll start from the Alberto, who's the furthest away from Pittsburgh.
Excellent. Thank you, Sudhu, for a very nice talk. It's great to see not just sort of the amount of work, but also it being organized in a coherent storyline. I have a, I guess, a general question about the role of tactile in these tasks, right? So tactile SLAM, like object pose estimation, object sort of shape estimation, object tracking. I see that as sort of like an intermediate task, right? So ultimately, a robot might want to do that for some reason. So in particular, in the way that you've sort of laid down a framework for how tactile is consumed or processed, I wanted to ask you if you think that there are things that might be missing, if there are choices that you've done explicitly thinking about sort of future downstream tasks, or if you think that you would have to sort of revisit certain choices there. I can make that question more specific, or I'm happy to leave it broad like that if you have ideas for.
Yeah. No, that's a good question. We've toyed around with this question of what downstream tasks are for like the past few weeks to months when I've been thinking about this proposal. And it's a lot of this talk is centered around tactile perception for tactile perception's sake, which isn't really, it's essentially a mean or an intermediate, as you put it, towards the downstream task. And but our focus really here was that to really pin down on the algorithms and the methods that we want to use. We want to focus on collecting data with a human in the loop, or we want to focus with collecting teleoperated data with good ground truth information, so we can isolate this problem. But yeah, going back to your question about what tasks or sort of what we would like to see out of this, and I'd love to get feedback from the committee on this as well. But something we've been thinking about is just when we have, say, a cluttered scene, if you think about a regrasping problem, or a K-ing problem where we have imperfect information of an object shape that we can get, say, from a visual estimate, or we have the same example of the mug that we have, but we have the handle of the mug occluded in the scene. So deriving that shape information while also ensuring that we have no fixtures on this object, so it can freely move around on a table, for example, could be certain downstream tasks that we can show. So reconstructing these, sort of, if we fix back on the idea of the mug, if we have a planner that can plan for grasping the mug at its handle, when we do not previously have information of where the handle is or what the handle is, could be one example of this. But that's also why I have the committee. So if you guys have other ideas, I'd be happy to take them as well.
Cool. No, I think that I mean it's a great motivation, and just sort of the idea of giving an object to a robot and the robot playing with it, sort of building a model of the robot. I think that that's something that many people have sort of thought about as a futuristic scenario. So I think that it's great to see the technology, building the technology to make that happen. It's an ambitious goal. Let me maybe ask a second question, a bit more concrete. Also the same direction of how tactile is processed. So in the tactile tracking problem, your sort of network or your framework goes from a tactile image from where you extract a depth reconstruction, and there from there you create you learn a tactile code, right? So a network extracts some kind of embedded code of that. But it seems like you made the explicit decision of going from the 3D geometric reconstruction to that tactile code instead of, let's say, more naively go directly from the RGB tactile image.
Yes.
Why?
Let me pull up this. Okay. So yeah, just to give context, I guess this is sort of the whole framework over here. So your question is more of why we went from images to 3D to embeddings rather than from images to embeddings.
Yes.
So yeah, so a lot of going from images to embeddings is, for example, work that Maria from your lab worked on for both going from image information to embedding information. But a lot of it is centered on the idea that what we essentially derive from this is like the images really from a visual-based tactile sensor have no meaning in terms of the colors and the illumination, apart from the task of deriving 3D information from them. So the whole idea of coloring them based on photometric stereo to derive, say, running Poisson reconstruction to get 3D information, we would tend to treat this more of as a point cloud problem. And so that's why we have this intermediate. And the another motivation for it is the fact that the tactile depth networks that we worked with previously worked pretty well in terms of transferring from simulation to the real world. And we also have, say, this is in the extended paper, where we have one comparison against directly using image space embeddings, comparing them against 3D. And we see that when we go to 3D and derive these embeddings with 3D convolution, we can actually get better results in terms of place recognition. Yeah, but yeah, there are two ways to go about this problem, and we chose to go about it this way.
Cool, that's great. Thank you. Happy to take pass the turn to someone else.
Okay, how about Mustafa? Since you're also external.
So thanks, Sudhu, for the talk. I think this is really impressive work. I particularly like how you phrase your work and relate it to sort of navigation SLAM and inspired from that. So I particularly enjoyed how you sort of pose the three challenges in this context of going from navigation slam to tactile slam. So the question about locality and coverage and inclusivity. So going back to sort of that insight, can you maybe pick one of your prior work and explicitly talk about I guess how these problems manifested in that particular problem and what were the design choices you made to actually address those and sort of contextualize like how those challenges were like addressed by the way you sort of address the problem.
Okay. So it's I guess I can talk about certain problems for if we think about the idea of how local this information is, I would say the 2D SLAM problem is a very interesting example of this because here, until we make contact with the object, we really don't have any priors on where the object is. So, and merely depending on 2D information that we get from the end effector of a robot is not sufficient for that. So that's one of the design choices there is we assume that we know where these objects are to start out with, without which it really becomes an ill-posed problem. And this ties into the idea of locality as well in terms of we'd also want global estimates that we get intermittently from a vision-based a visual camera that we can see in the scene. And those really tie into this 2D SLAM problem. And the idea of intrusivity here is all of these reconstruction problems, we're assuming that we have pictures on what the objects are. And relaxing those is what we would look towards when we're looking at the full SLAM problem. And the way I think about the intrusivity problem is we can think about having a generic camera that we're having to take a photo of the scene, but each time we take a photo, the scene actually moves, which is basically the analog that we have with working with a tactile sensor. But is there something I didn't pick up on yet, or I could also?
No, I think that makes sense.
Okay.
Thanks for your insights.
Cool.
And then I guess one other question
Yes.
I had was, I guess, more practical. So apart from your planar tactile slam work, most of the other work sort of focused on using gel size digit as the sort of the sensing modality. I guess I'm wondering, kind of, what was the thought process behind choosing that as the key tactile sensor, or maybe in hindsight, after doing all of this work, what do you think are the advantages? You in sort of the early parts of your talk, you mentioned other sensors like biotech and reskin. Do you have a sense for like the trade-offs? Is there a system where you would want to use all of this? Is that dependent on the task?
Okay.
What are your thoughts about that?
Yeah. So I found using vision-based tactile sensors to be quite intuitive in terms of when you draw the connection to a mobile robot problem where we have image information when you think about going from images to depth. So that's kind of where those key analogies come into play. And in terms of hindsight, I feel like so the way I presented this, it's the temporal order is actually different. We first worked on this problem, the 2D problem, before we actually worked with the vision-based touch sensors. But in terms of the flow and the story, it makes more sense to talk about this at the end. And hindsight's a weird thing in this case because a lot of the sensors, like you mentioned, like the reskin, those weren't around when I started doing my research. So a lot of this is evolving technology, which is what makes it interesting, but also makes it a bit hard in terms of you don't have baselines or benchmarks and things like those, and you sort of take it as it goes. But the biggest sort of benefit to working with, say, vision-based tactile sensors is, I think the price point right now is really good in terms of we're dealing with $300 sensors or $400 sensors compared to working with, say, a biotech, which is way more expensive than that.
All right, thank you. That's all the questions I have.
Okay, we'll continue with our internal committee members. Nancy.
Sure. So that was a wonderful talk. So thank you for that. I enjoyed it very much. And I think the work is very exciting. So to kind of build from Alberto's comment, I'll just start with a comment that my favorite downstream task is to have enough of a state estimate that I know what I'm trying to do will be successful. So if I'm trying to pick up a hammer, if I'm trying to reorient a wrench to use it, if I want to pull a single fork out of a drawer, how do I, I want to collect enough information to know I'm going to succeed. And I'll just make another comment. We did some blind studies where people would sort of feel for an object and pick them up. And so there we observed that the advantage of having a lot of tactile sensors all at once is that people would often just be like, tap their hand down, tap it down. They would sense parts of the object, like if it was a spatula, enough of it that they could then pick their hand up and then grasp it perfectly. So having a bunch of sensors distributed over a space can allow very fast actions like that eventually. So that kind of thing is cool too. The only exception to that was an iron. So people were very careful and they did the whole, it looked very much like their experiments. They sort of felt their way around it. I think because it was a little scary and it seemed dangerous. Okay, so that was just a comment. For the questions, I would like you to talk a little bit about how do you reason about uncertainties, in particular, how much uncertainty is too much before everything starts to fall apart. And I'll just start with that wide open question.
Okay. And here, when you talk about uncertainty, you're talking about you have less knowledge of where objects are.
Uncertainties from everywhere, right? So you have uncertainties from the robot and the object motion and the object shape, and you're moving around, and so it's quite possible that the information you're collecting is, if there's too much uncertainty, it's nonsense. You can't put it together to form any kind of 3D model in that. So I want you to talk a little bit about how do you reason about that? How do you, come back and say, okay, I have sufficient level of certainties about what I'm measuring that I can have a sense of one.
Okay. Yeah, so a lot of, if we take, for example, the planar tactile slam work, a lot of the uncertainties there is, so the domain is a bit more difficult to quantify in terms of you don't have very direct sensor specification models, and there are differences in terms of simulated pushing versus real pushing. So there's not exact analytical analogies. So a lot of that was sort of playing around with how different weights affect different, so for example, if we really enforce physical constraints on contact, how does that affect, do we get realistic pushing behavior for that? So sort of tuning those and figuring out those as part of the research. And in terms of how we can get good uncertainty for downstream tasks, I'd maybe point more to the particle filtering type non-parametric work that we have, which is we can essentially get uncertainty distributions that we have for these objects, say, go to this. Okay, so if we can, with more minimal assumptions on, we don't have Gaussian assumptions on where poses are, so we start out with essentially a bunch of points in space with a known model, and we can capture multimodal, bimodal distributions, and we can also measure what uncertainties of poses are in those spaces. The question over here
I
is,
think you had very good, like the objects were in a vice. they
yes,
were constrained, and I think you had very good tracking of your sensor. So when you move to the real robot, I think it's great that you're doing this, that you're trying to put everything together with a multi-fingered robot. But when you move to that, your object's no longer
yes,
constrained, and you don't even really know where the fingers are unless you're tracking them,
yes,
or where the object is unless you're tracking it. So
yeah,
how
which
do
is,
you bring all that in?
yeah, the beyond the point, a lot of this is not tractable just working with touch. So the thing that we would use to train on all of this is vision, which can give us say centimeter precision tracking for these objects that we can refine with touch. So you can think about if we have, say, going back to your example of like a hammer, we can have a canonical model of what a hammer is, but these are class specific, so they can change depending on what hammer you pick up. Starting from that, starting from visual tracking at say centimeter precision, that's where we would envision, say, tactile sensing comes into the loop to sort of get more fine-grained information, build this shape as you go. And also we think contact constraints are pretty informative because you get very accurate but local information as compared to what we get from cameras, which is more noisy but global reliable information. Yeah, it's a bit roundabout, but yeah, uncertainties are
I guess I have my suggestion for the robot project is that you motion capture everything possible so that you have extra tracking information. Just to ensure.
Yes.
Then you can, like, even though Lego is not so accurate.
Yeah.
Like a long time ago, this is not with the Lego, but with a different hand. We tried to just weigh an object with strain gauge sensors, and we're unable to do that. Completely unable to do that because we didn't have such good estimates of where the fingers were, and so the information we were getting back was complete nonsense. So just want you to be prepared for that and kind of have a backup plan.
No, yeah, that makes sense. And a lot of, at least we envision a lot of the prototyping will also be in simulation. So
Yeah.
we'd have
Then you would
So,
have perfect.
perfect estimation, but yeah, the challenge is closing the loop and putting it in real hardware, which,
But I do really like that you're trying to do that, that you're going to push things in that direction. That's great.
thank you.
With that, I'm gonna just pass one.
Yeah, by the way, very impressive body of work and great talk. I had a couple of maybe low-level clarification questions first. So
Yes.
one was in the NTM work. I was confused. Is the input to the neural network this embedding and local depth map predicted, or was that just something the network is trying to optimize to sort of match?
Okay, so, and here you're talking about the embedding that we get here.
Yeah. So if you go to any overview diagram of the NTM architecture.
Let me go. On the sheet going back. So here you're referring to the going from image to depth information, or is
So
it?
this neural model that you're optimizing, which is predicting STF, as you know, something like a neural field with
Oh, okay.
STF at each point.
I was confused about which one. Okay, now I got it. Let me go to.
So the first
Yes.
proposal.
Should be in the proposal. So, yeah. Here we are. Okay. Yes.
Yes, this lightweight neural field, is it a network being optimized to match these images, or is this also the input to it in some way? That I wasn't sure.
So it is a network that is optimizing for depth reconstruction loss.
Okay.
So you can think about if we have images and depth information that we get.
Yeah.
At each of these pose frames, we're optimizing for the depth reconstruction,
Okay.
which is essentially what we're optimizing for is SDF.
Okay. So sorry, if we just go to the previous slide, it's not as if these are input to the network, right? It's the network is optimizing something such that it matches this.
It is we are each time we compute a loss here, we're sampling directly from these images. So we're
Yes.
if I maybe it would be more helpful to have.
Yeah, but maybe just to clarify, all of these are used in the loss for the network and not as input to the network.
Yeah.
So that was my clarification. And the second was, so you mentioned in the proposed work that you'd be using the same data for the two proposed projects. But I thought the first project, which is more focused on reconstruction, would tackle this setting where there is a static object which can't
Yes.
move, and maybe related to what Nancy was saying, the more interesting questions for the second project in localization do maybe come in when the object can perhaps move as a result of the interaction. So is the plan to study the localization right now in the setting where this object is static and you are moving around it, or can the object also move?
Okay, yeah, that's a good question. So the I think a succinct answer would be we would like to collect the data in such a way that we can use it for both tasks. So if you think about so a lot of your the way you're thinking about it, there's objects in a scene that you interact with which move. But there can also be the flip side, which has, say, a fixed hand that's manipulating an object in a hand, which is also trying to do the robot to object manipulation problem. So essentially, we'd want some information on tracking for these objects, and we'd want some end effector information and image information that we can get from the robots. But yeah, it's I would say we haven't like converged essentially on the design principles of the data sets, but we'd want to do it in such a way that we can use it for both works. But like you mentioned, for the first proposed work, we could also have a scene where we have a fixed object on a bench by and us trying to reconstruct the object in touch.
But so in the second project, the aim is still to focus on settings where the relative position of the object with the can change.
Yes. So trying to relax the assumptions on us having to fix it down on a table.
Maybe one slightly broader question is, in a lot of the SLAM literature, at least more classically, this is just very scene specific, right? Like you learn or optimize something for each scene, and it's not that it's something you learned in one scene necessarily helps you in understanding other scenes. And I also think that's kind of true of the things we were talking about today, right? Like if I'm doing SLAM on this cup, and then you give me a new cup, it's not as if I've learned something generalizable that would help you. So just was curious on your thoughts on if, at some point someone wanted to pursue more generalizable versions of your systems, what would be good places to inject something that can help you generalize new objects and makes maybe inference faster, make you allow you to sort of guess on the shape of it.
Okay. Yeah, I think maybe to preface that, I can like all of the neural field work that we propose is essentially training a network from scratch at each iteration. So it's a continual learning problem. So there's no real question about generalization because we're just starting with randomized weights and then going from there. But towards generalization of these methods, one thing that I can think about is, and the reason we're inclined to work in the architecture of a lightweight MLP and things like those is you can bake in a lot of pre-training. You could do object class specific information that you can derive. So you can think about incorporating shape completion network information, something like deep SDF that does, where you essentially have a latent code on these are a set of hammers, or these are a set of scissors, for example, and then optimizing. So, but it can essentially be an optional point of this. But what, at least the reason we haven't chosen to work on class specific data is because we just want to go from image and depth information directly to 3D. So we want to keep it as generalizable as possible, but yeah. Thank you.
So maybe we can do a second round through the committee and see if there's any questions left. Alberto, do you have any?
I'm okay. I think that all of the questions I had have been sort of answered throughout all of this period.
Okay, Mustafa.
Same for me.
Okay, and Nancy.
Shubham
Yeah,
has.
not really a question, but even in the setup where you're using purely tactile information to reconstruct, not to say you should incorporate in this work, but if I grasp this cup, but I also know where my thumb is, and it gives me a cube of empty space, which is maybe a signal that isn't being used right now, which I assume humans can use.
Yes, I think sort of foreshadowing of that is the let's see where I can pull it up. But there's the let me just go to that. Yeah, so foreshadowing of that is this non-penetration type cost, which is saying we know where two pushes are. If we're not making contact with one of them, that's
and for the non-penetration, you can reason not just about contact points, but also about your body, right? Because as you're interacting with the object,
Yes.
your hand is moving through space.
So yeah, the lack of information is information. Yeah, that's a good point.
Yeah, I have a kind of related comment or question, which is, you use some kind of forced information, a little bit. I mean, maybe that's the extent of it, but I wonder if you use more, if you think it would be helpful. Force related information, in terms of building a model and where you are. It seems like it should be helpful.
Yeah, well, for working with the gel site and the digit, we don't really have force related information, because I think deriving that from the sensors in itself is an open problem right now. So we've chosen to just work with spatial information.
But again, in simulation, this is something you could, I'm not suggesting you add this to your
Yeah,
thesis, which is big enough already, but I'm just asking you to think about it for a minute.
okay.
Yeah.
No.
In simulation, you would have it. If you had it, what would you do with it?
Yeah, you could essentially do force closure type constraints, factor gravity, and if you're lifting something up, you know, the forces that are being equalized. But yeah, it does get complicated for multi-contact problems. But it's definitely
I
viable.
think you could do more with it.
Okay, it's definitely viable information. Yeah, it's a lot of deriving shear information is also useful in many cases, but you could treat it as you wouldn't think about the problem toying around with it, using shear information as a dot machine, for example. But yeah, there's definitely a lot we can do with that.
But Michael, I don't have any other questions.
Okay, sounds good. So let's open to the audience. Any questions?
You have to chat.
Okay.
I'll go first. So like, I guess you mentioned that, you know, like the disadvantage of using touch sensing is that it is pretty local. So the geometry you get is local, but advantage is that you get a more precise geometry.
Yes.
And other than using like gel side of digit, that is like just a touch sensing, there exists like some other sensors that have a proximity sensing capability before you actually get an interaction. So for example, Chris Atkinson have finger sense, finger vision.
Yeah.
So yeah, like before you touch it, you can actually have some like observation from it. And I believe that before, like so in your motivation, you have like you reach out, you do something. But in that scenario, maybe you just look at it and you have a good enough sight instead of actually need to touch it, and you get a global kind of observation just from that. So I would just like want to like ask you like, what's your thought about like, you know, embedded some kind of like proximity sensor, or maybe even just using vision like as instead of like a touch sensing scenario.
Yeah. So yeah, the way you think about say finger vision would be you'd have essentially two cameras. So you'd have one for proximity when you're far away from the object, and one when you make contact with it. We have tactile information that we can derive. So I think all those would need like they're essentially simpler versions of, or incorporating that information is more trivial once we have like one of these from like a foundation for this sort of setup. So here the way I formulated it so far is you have an external camera and then you have this, but I think all of these can neatly fold into that sort of method as well. But yeah, it's I haven't personally worked with any of those sensors, so I'm not sure, for example, how accurate the 3D information you can get from interaction and what the trade-offs are. Yeah, a big sort of question in all of this is that development of hardware is very contemporaneous with the work I'm doing. So it's always why not try this or why not try that? But yeah, that's a good question. Sorry.
So I'm coming from a like I have no knowledge about tactile sensing, so the questions coming through new. But like I guess like what I was wondering was like whenever you're introducing a new sensor, like I guess the question at least in my mind is like so that the existing domains or existing sensors, whether vision or let's say in that sense, like you already have tons and tons of data there. And so like you can exploit semantics, you can exploit like all the existing data to generalize and so on and so forth. And like so the new sensor that you add has to somehow be able to, because the new sensor won't have as much data, the new sensor will essentially have to do everything from scratch. And so like the amount of additional information that you give for any downstream task has to be more, or has to justify the like lack of data and lack of existing information out there. And like I was curious what, like how much, I don't know the state of the art in like any of these things. So like so I was trying to get a sense of like how much of a benefit does this offer, like essentially going off of the previous point of like which was like how much of an additional benefit does tactile sensing, especially if you're not accounting for the forces or like just for the positions, right? Like offer in terms of the accuracy of the measurements and like where exactly would be useful.
Okay, yeah. To get into your point about having like a large corpus of data that we can get and semantic information, things like those, I think a lot of this work kind of hinges on realistic tactile rendering. So using simulators such as Tacto or Taxim, a lot of the measurement models and things are things that we learned entirely in simulation. And the whole idea of that is data is now for free. We can manipulate and work with as many objects we can get, and we can build this. So I think in terms of a bottleneck, I think that has been alleviated by all of these, which is another benefit for working with, say, vision-based touch. Even four-stroke information on like modern simulators is good enough to sort of generalize to real-world tasks. So I think there's already a sort of playpen for getting that data. Yeah, I would say that it's getting closer to real-world natural images, but there's still a lot of work to be done. Sort of getting realistic physical simulations is still, a lot of it is really using PyRender and things like those to render out the physics from a perspective camera model for these, but moving towards actually modeling the gel and the deformation, which is a lot of work, I guess, Wenjin's lab is working on here as well at CMU. And any of that will help towards transferring it to a perception or downstream task.
Thank you.
There's also,
I have a question. So you mentioned like using like Gaussian process representation versus mirror representation. You mentioned that you can use more detail, see more detail. Would that be helpful in like figuring out, for example, more if you have a sphere where you can't really capture detail using the previous model? Is that like going to be helpful if you switch to this mirror representation?
Yeah. So one thing we want to do with the proposed work is do a more detailed sort of apples to apples comparisons between these methods. Right now, a lot of it are things that we've observed in terms of we get higher fidelity reconstructions working with MLPs. And a lot of it, my supposition is that a lot of it is that we're not using just like Gaussian kernels to sort of smooth over edges and things like those. And MLPs and nonlinearities that you can get from a network are more expressive in those tasks. But we do want to sort of give us a better comparison. So if I have a single frame optimization, I'm going to try to do that and compare that against a lot of the previous work I've done.
there's also a question in the chat. So how would the tactile perception work with deformable or deformed objects?
Okay, yeah, it's a lot of this work and domain kind of assumes that there's implicit rigidity in all the objects that we're dealing with. But from the experiments that we've done, so when we're collecting a lot of the manipulation data for both the localization problem and the mapping problem, there have been deformations in terms of like when we're dealing with sugar box, it's cardboard, and it deforms to an extent. And more often than not, we can ignore that and deal with the consequences and it works out fine. But the idea of deformable manipulation is, again, an open question here, because we're dealing with an elastomer-based sensor, and we're dealing with a deformable object such as if you take clay, then it's really more of an interposed problem in that case. But yeah, rigidity is kind of assumed in this work, at least to an extent. Abhijit?
This is a great talk, by the way. Thanks for this. In the same vein as Swami coming as an outsider to this field, one of the really exciting things for me, I think, is like the ability to sense and kind of act at the same time. And I think that's something you're getting into with your proposed work, right? Like with the SLAM kind of formulation. But can you talk about like what are the affordances of doing both of those things at the same time that maybe like your current work doesn't have, or like could it help in, like, for example, breaking symmetries with the mustard bottle example that you had?
Yeah, so in terms of a lot of the work that I've done, the proposed work, doesn't really delve into an active formulation of this problem, where we say we have a task towards reconstruction and we are directly trying to enable the robot to do that. We're mostly assuming that we have someone giving the instructions or some teleoperation happening in terms of collecting this data. And a lot of the motivation for that is we don't want to chew more than we can handle in terms of a problem. And we want to like kind of drill down towards a perception problem. But I think a lot of the representation that we talked about in terms of STF's implicit surfaces, you can do a lot of interesting active perception work on those. So you could use uncertainty information that we derive from this, essentially regions that we haven't figured out yet. We can directly drive the robot towards those, say, for example, follow the gradient of the STF. And there's a lot of implicit knowledge baked into this that we can use for a downstream task, which I cannot say the same for just working with point clouds, for example. So I think, I think one thing we want to think about is what are these downstream tasks we want to achieve, and what is a good sort of toy problem that we'd want to show this on.
Okay, I think this is a good time to wrap up. Yeah, so we'll have the committee meet and discuss. So if everyone else can please leave the room